Okay, so we talked about 2D equilibrium. Now let's move on to 3D stuff. Fundamental principles are basically the same. It just gets a lot more. It just gets a bit more annoying and complicated. So again, we're still working with the sum of the forces equals 0, the sum of the moments about any point being 0. So we can take those generalized formulas there and break them up into its x and y components, and we'll have the general 3D case. So as we talked previously, you can solve for a certain number of unknowns, and again, those can represent the reactions, the supports, connections, unknown applied forces, so on and so forth. We've got 6 equations to work with now instead of 3 equations, so we can solve for more unknowns. Of course, obviously, if we are working in 3D, we also have more unknowns that we're generally going to have to be solving for, so, you know, it is what it is. Different types of reactions. So you can have, for example, a roller ball here that's supporting it. Again, it's kind of like the feet of my chair here. It allows me to roll on the surface while still supporting the chair, ensuring that the chair does not fall through the floor. It has a force that it will be exerting on the body itself that is perpendicular to the surface, with no other forces given. So at least it may have an unknown. It may have an unknown magnitude, but it has a known direction. So ball or frictionless surface does the same thing. A cable is going to have a known line of action. Stuff that can have 2 force components. You could have, say, a roller on a rough surface. So if you roll this, obviously the roller is going to prevent. If you try to apply a force downwards, the surface is going to push back on the roller. If you try to push this thing this way, it's going to allow it to roll. But if you try to have a lateral force applied, then it is going to resist that movement, because it's then you're not rolling across the surface, you're trying to skid the skid the roller, so you get the friction component working there. Same idea, but a bit more stringent. Wheel and a rail do the same thing. And then we can have 3 force components. The table leg sitting on a surface. If you try to push on the table, it is going to resist that movement due to the friction between the table and between the leg and the floor it's sitting on. So here, the reaction again, can look like that, can look like that, can look like that, can act in all directions. Again, if it's still if it's sitting on the surface, the reaction from the floor to the leg still needs to, in the vertical direction, whatever orientation you happen to have that defined as, that's still only going to be positive. You're not going to have the floor grabbing onto the leg and trying to hold it down for something sitting on a rough surface. You can have that for ball and socket. So the ball and socket will allow the rod that's inserted into the ball and socket connection to rotate freely about, in whatever direction. But if you try to pull on it, it's going to resist it. If you try to push on it, it's going to resist it. In whatever direction you try to pull on it in. So that'll have 3 force components in any direction, while still not having any moments. Going to be universal joint. So something like this will resist lateral movement, and can also impose a a moment reaction about one of the axes. You know, if you turn this side, it'll force this thing to rotate about that axis. However, it'll still allow free rotation about this axis, and it'll allow free rotation about this axis. Fixed support obviously prevents all movement, so it is going to have a reaction in all of our possible ways that thing could move. Could have a hinge and bearing that supports a radial load only, so something like this could allow this hinge here to, the pin between the hinge here to kind of slide freely in and out. But obviously, it's still going to resist rotation. It's still going to resist lateral movement in this direction. It's still going to resist a lateral movement kind of out of the page here, and it is going to it's going to allow free rotation about this axis, but it's not going to allow any free rotation about this axis or this axis. So we could have bearings that do that. Pin and bracket, hinges that don't allow that sliding action to go on, so on and so forth. Other bearings, those can have 3 force components and 2 couples. So basically, the only movement that this support would freely allow is the rotation about this axis, about this axis, about this axis, so on and so forth. So let's get into an example. Here we've got this sign. It's got a uniform density, weighs 270 pounds force. Also weighs 270 pounds mass, assuming this thing's in Earth's gravity. But it is supported by a ball and socket joint at A here, and 2 cables. We got cable CE here, and we got cable DB here. And the point here is to find the tension in each cable, and then the reaction here at A. So what I'm going to do is, first off, I'm going to redraw this sucker. I redrew the diagram itself, kind of in what I'm defining here as the XY plane and the YZ plane. So kind of looking at the side of the sign, and then looking at, kind of directly along the length of the sign, with up being up in both these orientations, which I think kind of shows the helps show where the forces would be applied a bit easier. So took that and basically made a free body diagram from it. So in our XY view here, the kind of forces that we'd be able to see would be the forces in the X direction. So we're going to have an AX here, so basically a force support from the ball, the hinge. We're going to have an X component of the tension for this cable here from E to C. So that's this cable here. And we're going to have an X component of the tension for this cable here from B to X. So that's this one. That's this one here. Sorry, B to D. So those are our X components. We also see the Y components on this XY diagram. So again, we've obviously got the weight, because that X downwards. We've got this the Y component of the support at A, and then we've got just the vertical components of those two tensions that we already talked about. This other view here, looking at the sign kind of from the end, again, we can see the weight. Some of these views, some of these forces kind of overlap in this view. So if we're kind of looking down the length at the top of the sign here, AY, BY, and EY, they kind of get applied at the same spot, and they're acting in the same direction. So those overlap. BZ here, again, because that's this one here. That one's acting to the right here. So again, based upon our coordinate system, that'll be a negative Z component. And then the AZ and EZ, again, are applied at the same point, but overlapping a little bit. So can't really show them separately on the graph. So again, kind of based upon the fact that this graph has all those forces are acting through the same point. You know, the line of action for all those forces that we can see are through that point A there. They converge on the same point in this, at least on this graph. That one's not going to be very useful to us. So I also drew a top-down view here. So just looking at this thing top-down. So again, the X direction here is going to be kind of located downwards here. So we're basically, and we're going to have the Z direction still positive that way. And again, that's still, that'll basically, we've got a bit more information here that we're able to kind of leverage for when we start to try to solve this. So again, we got the X and the XZ axis graph. So we got the X and Z components of the two tensions and of the reaction at A. So, like it says here, the tools that we have at our disposal, we've got the various sums of the forces and the various sums of the moments about the three axes that all need to be equal to 0. So I'm going to start here I'm going to start by taking a moment about the y-axis. So we're going to take a moment about the y-axis by looking at the forces that are acting in the XZ plane. So kind of just looking at this one here, what we're going to have here, it's the same graph I just did, and we're going to take our point about. I'm going to take the moment about point A, basically just to eliminate a few variables from our equation. So we've already got the. So basically that means that when we take our moment, both of the A forces disappear because they act through the same line of action as the point their line of action intersects through that point, as do these two x components of the tensions. So the only forces that we end up on this graph are the EZ and the BZ. If you may be thinking about the other forces that weren't shown on this graph, like the weight, the y components, those also don't affect. They're not shown on the graph because they're coming straight in and out of the page, but they also don't show up in the moment about the y-axis because they are acting parallel to the y-axis. So those aren't going to cause any rotation about the y-axis. They just, they don't cause rotation against it. They just push against it. So that's we got those ones, and then the line of action that goes through A get eliminated from our calculation. So taking the moment here in the y-axis at A, that just gives us looking down here, we've got we've got the two tensions. Those tensions, again, they are acting. They are acting in different directions here. When we're looking kind of top down at them. Essentially, thankfully, when we add them together, I guess I should have added the equals 0, but that's relatively easy to solve for. So we got this BZ times the 8 feet between here and here, minus the EZ times the 6 feet from here to here. That allows us to solve for BZ. So now we've got the Z component of the tensions in terms of one another. So we can go a bit further than that, because we know that the Z component of the tension of the tension in the cable is a function of the unit vector and the overall tension in the cable. So we can solve for the unit vector. So for the cable BD, our unit vector is going to be this. And that's just based upon, we've got when we move from B to D, we've got a negative 8 foot movement in the x direction. We've got a plus 4 foot movement in the j direction. Now we've got a negative 8 foot movement in the k direction. So we've got that. We need to find what the total distance from B to D is. So again, that's just Pythagoras' theorem. So that's 12 feet. So we can just solve for what the BZ is in terms of the tension in the cable from B to D. So that ends up being minus 8 over 12 TBD, or minus 0.666. And likewise, we can do the same thing for BX and BY. Similarly, same deal for solving for our unit vector for EC. So we got our distance here, again, just based upon the total. The total is distance from E to C is just based upon using Pythagoras' theorem on the rectangular components of its displacement, and then just the our I here, that's just going to be the 6 over 7, the minus 6 over 7. The J here is the plus 3 feet from here to here, over 7. K here is just based upon the plus 2 feet from here to here over 7. So we got our, that allows us to define the components of our tension, the rectangular components of our tensions for both of these in terms of of each, well, in terms of the overall tension. And we also got this relationship here that we solved for the BZ in terms of EZ. So we can just take, we got the BZ here, we can plug in this value here that we solved BZ for previously, and we can plug this value here, our unit vector times our tension in EC, our tension in the cable from E to C, and then that basically allows us to solve for the tensions in terms of one another. So that basically means that the tension in B to D ends up being something that we can that is a bit under a third of the tension in E to C, 0.324. So that means that basically we can take those 6 rectangular components on these diagrams, and we can put them all in terms of a single variable. So we can solve all of those in terms of either TEC or TBD. I chose TEC, but it's relatively simple enough. So just plug and chug. Bx ends up being equal to negative 0.216 TEC. By is equal to 0.108 TEC. Bz, again, negative 216 TEC. Oh, by the way, if you're wondering why when I put the when I was doing this relationship here, why I put 0.666 TBD instead of negative 0.666 TBD, that's because when I was solving for the BZ in the first place, I used the BZ oriented in the proper direction anyways. So the negative or plus sign here tells us the directionality of BZ, but I'd already accounted for that on the free body diagram. So anyways, these other ones, you can solve for those. So now, basically, we started off with what looked like 6 unknowns, and now we've got them all in terms of a single unknown. We are making progress here. So, what's the next thing to do? Let's take another moment. So I'm going to take a moment about the z-axis taken today. So again, that would be based upon our diagram, the free body diagram in the xy plane. So for the purposes of this calculation, I drew an amended free body diagram that only includes the forces that would be included in that calculation. So any of the other stuff either is acting parallel to the z-axis or passes through A. So I didn't bother drawing the stuff that passes through A. So that one is relatively simple. So the sum of our moments about A got this 4 feet times our weight, and that again, that's going to cause a clockwise rotation, so it's going to be a negative moment. Got the 6 feet here from A to EY times the magnitude of EY, which we're just pulling from here. So that gets plugged into there. And then we got the 8 feet from A to B times the magnitude of Vy pulled from there. So that basically allows us to solve for TEC. So we take the 6 feet times that and the 8 feet times that, add those two things together, we get 3.432 feet TEC, and move this over to the other side of the equation. We end up getting 180 pound-feet. So we can solve for TEC just by dividing by our 3.432 feet, and that gives us 304.7 pounds. That's the tension in this cable here. This cable here. This cable here. So we got that. The next thing to do would be to solve for the tension in the other cable, because we already solved for that in terms of the other cable. So it's just taking this value we got here, multiplying it by what we found this relationship is right here. So that gives us 102 pounds. So we've taken our moments. Like I said earlier, taking a moment about the x-axis isn't going to be very useful here, because basically everything goes through that A point, or at least if we take it about, say, a different point, it'll be useful, but the calculation will get really complicated and annoying, so let's not do that. Instead, let's just move on to the sum of our forces. So, the total forces in the y direction, again, needs to be equal to 0. So, well, we got a reaction support at y. We got the weight, again, acting downwards. We've got the y component of our tension of our EY and of our BY, and we just add those things together, and allows us to solve for AY. So that'll be 101.3 pounds force. Oh, yeah. The force in the x direction, same deal. Got the AX support reaction there, and then we've got the X components of the two tensions. So I kind of just group those together so we can group those together here, because again they're both some ratio times 314.7 pounds. So anyways, simple enough to solve. Eventually we just find that our AX is going to be 337.7 pounds. And then do the same thing for the Z direction. So we've got our Z axis reaction. We've got the the terms for our Z components of the E, Z, and the BZ. Now again, we're subtracting here because the EZ's acting in the positive Z direction, the BZ is acting in the negative Z direction. So that one ends up being AZ ends up being a negative 22.7 pounds. So I just kind of quickly redrew the original diagram here. So we got the two tensions. I got the positive AY reaction. You get the positive AX reaction, and the negative and you get the negative a Z reaction. So pointed in this direction because the positive Z direction is this way. And that's about that. So again, similar concepts to what we saw with the 2D stuff, just kind of gets, it's more annoying and it's more tedious. And sometimes you got to be a bit more careful about picking kind of where you take your moments about, what axis you're taking your moments about.